Hi, my name is Jaden Pauling, and this is Lab 5, Faraday's Law. The purpose of this lab is to observe Faraday's law of time-varying magnetic fields and how it affects the fall of a magnet. We will do this by using the key physics concepts, Faraday's law, Lenz's law, and the principle of magnetic flux. In this experiment, we recorded the time that it takes a magnet to fall through an aluminum tube using a video. And using that video, we would scrub through the frames and record the timestamps to determine the initial time that it entered the tube and the final time that it exited the tube. Using these initial and final times, we were able to calculate the time that it took to fall through the length of the tube. The length of the tube that was used was 30.5 centimeters. The thickness of the foil was 0.8 centimeters. The outer diameter 4.5 centimeters. The inner 2.3 centimeters. And just for thoroughness, the thickness of the cardboard was recorded to be 0.4 centimeters. I took the magnetic moment of the bar magnet to be 2.818, which was calculated in a previous lab. During the experiment checkpoint, we addressed a few questions. Why can't we use a ferrous tube, for example, a steel pipe? Ferrous materials are the only objects that are physically attracted to magnetic fields. Therefore, we can't use a ferrous tube because it would be magnetized when approached by the magnet. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? The magnetic flux in the tube creates the magnetic force on the bar magnet, which causes it to fall much slower than it would when falling in free space. In the coding portion of this lab, we used a previously created function that calculated the magnetic field created by a dipole and a function that calculated the magnetic flux through a cross-section of pipe. In addition to that, we also applied the momentum principle in order to create a velocity and position update. The resulting code created this graph, which depicts the bar magnet approaching a constant velocity, which indicates that the magnetic force on the bar magnet is increasing until it is equal and opposite that of the gravitational force. Things that may have affected the differences in T values include the quality of our tinfoil, meaning that in between each run, the tinfoil could have become crumpled more in some places, which would have increased the magnetic flux through that area or the induced current in that area, as well as the calculated mu value from our previous labs, as well as experimental area errors in calculating the time. End of lab questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? If there was no resistance, the induced current of each ring in the tube would have an additive effect, meaning that it would not dissipate as the magnet is passing through it. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The induced current is only created in a closed loop, per Faraday's law. Holes or slots in the tube would break the closed loop, so there wouldn't be any current. Overall, there would be less current in the tube to oppose the magnetic field. In conclusion, magnetic flux creates curly E fields that generate current, which in turn produces a countermagnetic field. Both experiment and computer models show that the aluminum tube slowed the magnet's fall by creating a current that produces this countermagnetic field. Thank you for listening and have a good day.